So we're talking about section 2.4, continuity. I've already assigned 4 problems from this section. I'll do a couple of similar problems. One problem you're not going to like. Get over it. All right? You still have to be able to do it. So you're just going to go and find all my old continuity quizzes, continuity test questions, etc. Okay? So what does it mean to be continuous? So y equals ln of x is continuous. Y equals sine of x is continuous. What do you think? What's your gut say?
On either the y or x axis, then you never have a point where you don't have a value, and it's continuous.
I like that. I like that. It's all we need is that second half. If I've got no point, if I have no point removed from any part of my graph, it's continuous. It's like a roller coaster. You don't want a hole in the tracks, right? So that's all I need, but our actual formal definition, and Autumn, you said that. You said more than you needed. But that's beautiful what you said. So our definition of continuity is the limit is x goes to c, of f of x is f of c. And that's a real number. If that's true, the function is continuous. So you can notice something. What did I do with C? What did I do with C to F? To the function. I plugged it in. So I can plug in everywhere on the function. Anytime I want, I can plug in the value and I'll get the height. It's that simple, right? So will I ever need a replacement function for this one? No. But of course we trick you into, we start to use piecewise functions, which are horrible if you remember pre-cal. Yeah. So start thinking about these doing piecewise functions. What has to happen here? Yeah, if I'm doing pieces, I'm doing a piece to the left and a piece to the right, right? They have to be the same. They have to match up. Yeah, so same. So here's our little checklist, right? So we say here, f is continuous at x equals c, right? If the limit of f of x is f of c, and that's a number, a real number, right? So here's our step-by-step. Find f of c, find the limit as x goes to c from the left and the right of f of x, and make sure step 1 equals step 2, and then you know it's continuous. Pretty simple, okay? When I give you step by step, you should put them on your formula sheet, right? Because if you get nervous, you're going to forget. What do I do, right? So you want a list of things that what do I do in this type of problem? So, but this is it. So let's do a couple problems. I might not finish this all today, but of course you'll be able to do the first 4 homework problems. Let's look at number 24 in the book. It says, can you remove the discontinuity in this function? So this is number 2.4, number 23. Oh, 24, thank you. F of x is equal to x cubed minus 8 over x squared minus 4. And we want to know at x equals 2, is it continuous? Well, I can put in the 2 right away, right? Yes, I can put in the 2 right away. So if I put in 2, I get what? 8 minus 8 over 4 minus 4. I get 0 over 0. So I can't, right? So there's a hole in the curve there. Yes? So then it's asking me, can I patch up the hole? And with what height should I patch the hole? So we kind of have some kind of line, and at 2, there's a hole in it, right? So what point will patch the hole? You with me here? So what I have to do is figure out that limit and then patch the hole with it, right? So obviously we're going to work on star, which was what? X cubed minus 8 over x squared minus 4. Who's got the factoring for me on x cubed minus 8? X minus what? 2 times? Nice. And my x minus 2's will cancel. So I have this function now is my replacement function. Is everybody following what I'm doing? The question's asking me, what happens at 2, right? And we're really interested in continuity. Is it continuous or is there a hole in it? 0 over 0 can't happen, right? We know there's a hole there, but we know how to patch that hole. We find what the limit would be, right? And then put the hole on the manhole cover. Put the cover on, right? So now what do we know? The limit as x goes to 2 of star is 2 squared plus 2 times 2 plus 4 over 2 plus 2. So 3, yes? So what we're going to do is we're going to create a piecewise function, and we're going to say use the original function x cubed minus 8 over x squared minus 4 if x is not 2, and if x is 2, use the height 3, and we will patch that hole. You with me? So in those first 2 homework problems in 2.4, you can do them right away. It's going to ask you what happens at 2. One might work, and you know it's continuous already. One might not work, and you're going to figure out how to patch the hole. Question. So, but there is no little post-voting. Oh, sorry. How are we doing? We okay? Yeah, with the definition?
Yes.
Step by step?
Yeah.
Okay, here we go. Yes. You see that little timer in the left corner? Yeah. All right, we ready? The question is this problem continuous? The question is this problem continuous? So I'm looking at number 40 here. (2.4) number 40. And I've got a piecewise function, f of x equals equals a two-piece function 1 minus x squared if x is less than or equal to 1. And I'm going to use ln of x if x is greater than 1. So it's a two-piece function. It's two different machines. One of them works left of 1. One of them is going to be in charge right of 1. Does that make sense? Let's look at how to graph this on Desmos. So I can use y, I can use f of x. Doesn't, in this case, I don't think it matters too much, but my first function was 1 minus x squared, correct? And I want to restrict this with a curly bracket. X, what was it, less than or equal to? I forget already. Yeah, less than or equal to 1. I get the less than or equal down here. And it shows me only that piece of the function. You with me? My other function was ln of x, and I want that curly bracket for x is greater than 1. Does it look continuous? Does it connect? Yeah. So it's continuous, we know that, but we're going to verify with the definition. This thing is not differentiable. That one is not differentiable. What do you think I mean by differentiable? Say again? No. Differentiable. Exactly. Differentiable means the derivative can be there. Slope can be there, right? But the problem, like this one, the slope on the red curve is negative. The slope on the blue curve is positive. So at 1, the slopes don't match up.
They cannot.
They do not match. The slopes don't match.
Not.
That's so I can't make a derivative at that point. I don't know which slope to use. That's a little bit later in the course, so, but yeah.
Which is the one for the restaurant?
Okay, so a derivative is a limit, right? And a limit doesn't care about getting to exactly.
Oh, and when you're approaching from the right, it's using that positive.
Exactly. Okay, let's show that it passes the definition for continuity, right? So step 1, find f of 1, right? Which machine do I use, the first machine or the second machine? First machine, how do you know? Because it says equals to 1, right? So I'm going to use 1 minus 1 squared. That's 1 minus 1 is 0. Obviously, we get the height of 0 when we were looking at our Desmos curve, right? Step 2, find the limit from the left and from the right of 1, right? So the limit as x goes to 1 from the left, we already figured that out, right? I'm using the machine of 1 minus x squared, and I get 1 minus 1 squared is 0. So the limit from the left is so far okay. I need the limit from the right to match the 0 as well. When I'm going from the right, I'm using the ln of x function, and I get ln of 1, which of course is 0. And so I know that the limit as x goes to 1 is 0. I know f of 1 is 0. I know this and this match, right? So since the limit as x goes to 1 of f of x equals f of 1, which is 0, f is continuous. Does that make sense? I check the actual height of the function. Then I check the limits as I get to that x value, left and right. If they all match up, good. Continuous. If any one of those fails, not continuous.
But then.
Then I can patch a hole sometimes. I can patch a hole when it's just a single point removed, but not if there's a jump. I don't know where to put the cover on the hole there. Why are we interested in continuous curves? Because they're easy to deal with, right? So if you're looking at like a heartbeat, what happens if it's not continuous? Someone's dead. Like my girlfriend has an arrhythmia, so sometimes her heart will go crazy, but it doesn't stop. It's the stopping part that we're worried about. Let's look at another one. So that's one type of function. Is it continuous or not, right? Or three types of functions. Can I find the hole and patch it? Can I tell if it's continuous? And then lastly, let's make something continuous. So I'm looking at here on 2.4, and this is our last problem today, which is nice. Number 46. It's almost Friday. I've got a two-piece function of cx squared plus 2x for x less than 2, and I have a x cubed minus cx for x greater than or equal to 2. C is a variable. On Desmos, it would be a slider, right? Yeah. C is a constant. So let me put this in to Desmos first. Cx squared plus 2x oops. Come on, Robert. For x is greater than 2, add slider C. And then my second function x cubed minus cx for x is less than or equal to 2. So there it is. And obviously I'm interested in it too. What do I want to happen? I want them to connect. So I got to find the value of C. So it's kind of nice to have the slider here. See if I can get them to connect at all. Yeah. Yeah, so it looks like it's almost connecting there, but it looks like it will work, right? So we just have to find the right value of C. So here we go. I have to find the limit from the left to be equal to the limit to the right to be equal to the function all at 2, right? Say it again? Cx plus 2x. X is less, oh yeah, you're right, I switched them, thank you. And then greater and equal to 2. Sorry, it's just going to switch the two curves. Sorry about that. Still want the same idea, right? I want those guys to match up. Thank you. So I need the limit as x goes to 2 from the left. Which function should that be? First function or second function? First one, right? So of cx squared plus 2x, I need that equal to the limit from the right, which is my x cubed minus cx. And I need all of that equal to what? To the second one, yeah. So I get 2 cubed minus c times 2. So 8 minus 2c. But guess what? That is my limit from the right, right? Because that's where I got the equal sign. So I just have to check this other limit and find c. So I need the limit as x goes to 2 from the left of cx squared plus 2x to be equal to 8 minus 2c. So what do I do on the left? Plug in what? 2. So I get 4c plus 4 equals 8 minus 2c. So I get 6c equals 4, or c is what, 2/3? We want to check it and then make a conclusion, okay? So let's check it. Let's let c equal to 2/3. Oh, look at that. Nice. And then conclusion, yes? With c equal to 2/3, f is continuous everywhere. Here's the thing, is this calculus was discovered and built upon long before there were calculators, computers, things like that. So what we're doing in this class, in this modern time, is we're saying, hey, we have technology, let's verify our calculus is right? Right? And so what I'm trying to get you to do is do your calculus and then know it's right by the graph. And what I'm saying is that way you can start to trust the calculus. You can start to trust what you're doing in the calculus class to know it's right. And of course, if I went back in and put this 2/3 in, guess what? And I did my piece of what's the value of the function, what's the limit at 2, do they match up? Yeah. So that will be okay. All right. Have a great day. See you Friday.